Welcome back to our channel. We have already finished half of the chapter. Let's continue with its next half. Till now we'll be dealing with only two statements with a single connective. Now, we'll be dealing with more than two statements with two or more connectives. This brings us to statement pattern. Let's find out what is it. Let P, Q, R, S be simple statements. A compound statement obtained from these simple statements by using one or more of the connectives like and, or, negation, implication, double implication, is called a statement pattern. For example, P, if and only if, not Q, and R, if and only if, not S. To determine the truth value of statement patterns there are two ways. First, by constructing truth table, when we have to consider all possible truth values. Second, without constructing truth table, when certain truth values are given. Constructing truth table. A truth table contains 2 raised to n rows and m plus n columns, where n equals number of component or substatements, that is, P, Q, R, S, counted only once, and m equals number of logical connectives, that is, and, or, negation, implication, or, double implication. Note that negation of P, if and only if, Q, and not P, if and only if, Q, are not same. There are two methods to determine m. Steps to determine m, using the first method. Step 1. Count each connective involved in the statement pattern only once. Step 2. When a connective is repeated, observe the statements connected by, or, to the repeated connective. Step 3. If the statements connected by, or, to the repeated connective are identical, then count that connective as 1, otherwise 2. For example, find out n and m for the following statement patterns. P and not Q implies not P and not Q. Solution. N equals 2, where P and Q are counted irrespective of negation. Step 1. Total number of connectives equals 3, that is, and, not, implication. Step 2. And is repeated twice and negation is repeated thrice. The statements connected by both the ands are not identical. The first statements connected by both the and are different, which are P and not P. As the first statements are not identical, no need to see for the second one, as both the connected statements must be exactly identical to count that connective as 1. Therefore, number of and equals 2. So, now, total number of connectives equals 4, which includes 2 and negation, implication. 2 out of the total 3 statements connected to negation are identical, which is not Q and not Q. 2 of the statements will be counted as 1 and the other negation will be counted separately. Therefore, number of negation equals 2. So now, total number of connectives equals 5, which includes 2 and 2 negation, 1 implication, thus, m equals 5. This is the first method that we have used. We have one more way of finding out m. It is the splitting method. Now let's find out m by the second method, which is by splitting the statement pattern. Just like BODMAS rule, first split the two brackets. On splitting it, we get our first logical connective, which is implication. Now, we need to split each of the following brackets separately. On splitting the first bracket, we get our second logical connective, which is and. On splitting the second bracket, we get one more and. Now, before counting this another and as one more logical connective, let's find out whether the statements connected by both the ands are identical or not. Observe that the first and has P as the first statement and not Q as the second statement, while the second and has not P as the first statement and not Q as the second. Here, the second statements are identical, that is, not Q, but the first statements are not identical. Since both the connected statements must be exactly identical to count that logical connective as 1, both the and will be counted separately. Remember that till now we have 3 logical connectives in total, which are 1 implication and 2 and. Note that always count the number of negation in the last and not in the middle. Here, at the end we can see 3 negations, but observe that not Q is repeated once and therefore it will be counted as only 2 negations, which are not Q and not P. Earlier we had 3 logical connectives. Thus, m is equal to 5. By using the previous method also, we got the same answer. You can use both the methods, but the first method is less time consuming in exams. Similarly, you can find out m for the second statement pattern. First, try solving it yourself without seeing the solution. And after solving it, look for the solution displayed on the screen. Summing up, in splitting method you need to remember 3 simple rules. Always split the brackets first. Always count the number of negations in the end and not in the middle. And lastly, be very careful while counting the number of logical connectives, especially whenever a logical connective is repeated. A statement pattern which has all the entries in the last column of its truth table as T is called tautology, represented by small t. A statement pattern which has all the entries in the last column of its truth table as F is called contradiction or fallacy, represented by small f. A statement pattern which is neither always true nor always false is called contingency. All the possible combinations of truth values while dealing with 3 statements, namely P, Q and R, can be found out by this simple diagram. Write T and F in the first column and all possible combinations of truth values while dealing with only 2 statements in the second column. Now, draw a table with 3 columns for 3 statements, P, Q, and R. Look at the diagram and start connecting T in the first column with all the elements in the second column one by one. Simultaneously, write it down in the table in rows. Thus, we get TTT, TTF, TFT, and TFF. Now, connect F in the first column with all the elements in the second column. We get FTT, FTF, FFT, and FFF. Make sure that you don't change the order of any of these elements to avoid confusion. Let's begin with exercise 1.6. Prepare truth tables for the following statement patterns. The first one is, P implies not P or Q. Here, n equals 2, thus number of rows equals 2 raised to n, which is 2 raised to 2, that is 4. Plus 1 header row. M equals 3, thus number of columns equals 2 plus 3 equals 5. Given below is the truth table for the first statement pattern. Similarly, solve others. Try solving it by yourself first. Then pause the video to check the answer. Examine whether each of the following statement patterns is a tautology, a contradiction, or a contingency. Draw truth tables for each of the given statement pattern. And then look for the solutions displayed on the screen. Just like the previous ones, solve these. Then pause the video to note down the solution. Prove that each of the following statement pattern is a tautology. Again, draw truth tables for proving it. The solutions are given below. Pause the video for the solution. Prove that each of the following statement pattern is a contradiction. Again, draw truth tables for proving it. The solutions are given below. Pause the video for the solution. Show that each of the following statement pattern is a contingency. Again, draw truth tables for showing it. The solutions are given below. Pause the video for the solution. Using truth table, verify P or Q and R is equivalent to P or Q and P or R. Here, follow the same process as in the previous ones, but the only difference is that we need 2 header rows instead of just 1, for numbering the columns as well. Pause the video for the solution. Prove that the following pairs of statement patterns are equivalent. Follow the same procedure as in the previous question. Pause the video for the solution. It's a wrap up for today. Thank you.